Welcome to my physics Lab 2 on projectile motion. The purpose of this lab was to study the motion of a projectile using Newton's second law. This was done by comparing a computational model built in GlowScript and by analyzing observed results using the tracker software. Our observed results were compared to two different computational models, one that considered drag force and one that did not account for it. Our system was the paper ball and the surroundings are the air and table. From the results, we found that the computational model, when considering drag, underestimated the motion of the ball, while when not considering drag, overestimated the position of the ball. We also found that the model's inclusion of drag could be verified by the fact that drag force curve was under the curve without drag force. Newton's second law defines the net force as being the derivative of momentum. From this, we can derive the velocity update formula. Using these formulas, we can build our computational model that does not consider the drag force. The force of gravitation describes the attractive force that brings two objects together. This force can be modeled by the second formula to the left. Setting this expression equal to mg, the weight of the object, we can derive the gravitational force due to gravity on Earth. This is used in the calculation of F-net in both computational models. Finally, drag force describes the resistive force that acts opposite to the motion of the object. This force can be described by the third formula to the left. This formula was used to calculate F-net for the computational model that considers drag force and gravitational force. Here is the observed motion of the ball. As you can see in the video, a paper ball was thrown from the left to the right with a parabolic motion. Each red diamond represents the center of mass at that point. In addition, we used a meter stick as a calibration so the tracker software could properly predict the motion of the ball. Over time, at a time interval of 0.033 seconds, the x and y coordinates of the ball are generated. Here's the computational model without the consideration of drag. F-net was calculated using the mass of the ball and the acceleration due to gravity. Since this force acts only in the y direction, we multiplied the expression by j hat, which is 0, 1, 0. Since there are no other forces acting on the paper ball, F-net was set to W. Then, we updated the code with the system specifications such as the mass of the ball, which was 0.045 kg, and the initial position and velocity of the ball. The initial velocity value was calculated using the first 2 points from the table generated by tracker. Since there is no drag for this computational model, the proportionality constant for the drag force is set to 0. Now here's the computational model with drag. There were only two main edits to this model. The first edit was the proportionality constant. Instead of 0, the constant had a value associated with it, which in this case is 0.05. This allows us to evaluate the motion of the ball using drag. Then, we edited the way that we calculated F-net by adding the calculation for the drag force, which uses the proportionality constant that we edited earlier. Finally, we add this newly calculated value to the F-net variable. Here are the final results that we collected from the observed trajectory and the results collected from the two computational models on GlowScript. As you can see, the drag curve underestimated the position of the ball, while the no drag curve overestimated the position of the ball when compared to the actual observed position. Now let's talk about the sources of error. There were three main sources of error in our lab. First was outside forces. There were lots of forces outside of the force due to gravity and the drag force that we didn't consider. One example of a force that was not considered were the gusts of air from the air conditioning unit. Ball tracking. In our observed results, there was no way for us to make sure that the video was taken without any angle, which means that there could have been a z component to the motion of this ball. Finally, the shape of the object was irregular. Not having a perfect ball could have influenced the trajectory of the paper ball. Now let's discuss the what does it mean questions. Terminal velocity refers to the instance when a falling object reaches a maximum speed where the ball will no longer go faster than the terminal velocity that is reached. In this case, the computational model that predicted the motion that considered gravity and drag was the one that predicted terminal velocity. This is because the graph is nonlinear and eventually plateaus, unlike the computational model that considers only gravity. The plateau is characteristic of the object reaching a maximum velocity. Now let's discuss the what-if questions. If the ball was thrown straight up into the air versus being thrown in like a projectile, it would take less time to reach the ground. This is because all the initial velocity is in the y direction. Meanwhile, in the projectile motion example, the initial velocity is distributed amongst the x direction as well, which does not contribute to the projectile reaching the ground. Thus, since all the velocity is distributed in the y direction for a projectile that is thrown straight up into the air, it will reach the ground faster compared to the projectile.